Whatever you ate this morning is already gone, not sitting in your stomach, taken apart. Glycolysis split the glucose in half. The Krebs cycle finished the job. And here's the strange part. After all that dismantling, the cell has barely made any usable energy yet. What it holds instead is a small handful of electrons, carried by two molecules, waiting. Almost everything you'll run on today comes from what happens to them next. For 3 episodes, we watched sugar come apart, and so little ATP to show for it. That's because those earlier stages were never really about ATP. They were loading carriers, NADH and FADH2, with electrons. This final stage is where the carriers are emptied and where most of your ATP is finally made. It also hands the empty carriers back, so glycolysis and the Krebs cycle can keep running. Stop this stage, and everything upstream jams within moments. This is the reason we breathe at all. To watch it happen, we go inside the mitochondrion, and then in further. Its inner membrane doesn't lie smooth. It folds over and over into deep pleats called cristae, like a curtain gathered tight. Those folds multiply the surface, and the whole chain is packed along them. Bacteria manage the same trick with no mitochondrion at all. They simply run it on their own outer membrane. Same chemistry, older address. Set into that membrane are 4 large structures: complex 1, 2, 3, and 4. Between them move 2 smaller carriers, ferrying electrons from one to the next. Ubiquinone, drifting through the middle of the membrane, and cytochrome C, sliding along its surface. And off to one side stands a 5th structure we'll come back to at the end, the one that actually makes the ATP. Here's how it begins. NADH arrives at complex 1 and lets go of its electrons. The electrons from FADH2 come in at complex 2 as succinate is pulled apart. From both doors, they're handed to that same drifting carrier, ubiquinone, which shuttles them onto the next stop. Now watch the direction. Each new holder grips the electrons a little more tightly than the one before. There's no push from behind. It's a pull from ahead, each step wanting them a bit more than the last. So they only ever travel one way, deeper into the chain. And every handoff does work. As the electrons pass through complexes 1, 3, and 4, each one shoves protons, single hydrogen ions, from the inside of the mitochondrion out across the membrane. Complex 2 sits this part out. It passes electrons along, but pumps nothing. Slowly, one side of the membrane grows crowded. This is the part worth slowing down for, because it's where the real energy is stored. And it's almost never where people expect. It is not held inside a bond, waiting to snap. It's held in the difference between the 2 sides of that membrane, a crowd of protons packed against one face, all of them pressing to get back across. That imbalance has a name, the proton motive force. Energy, held as an electrochemical difference, a crowd wanting to even out. But none of it moves unless something waits at the very end to take the electrons off the cell's hands. That something is oxygen. At complex 4, the electrons finally land on it. Oxygen accepts them, joins with a few loose protons, and becomes water. Ordinary water, the kind you'd drink. This is the only reason the whole line keeps flowing. Take the oxygen away, and the electrons have nowhere to go. They back up, the chain stalls front to back, and that, at the scale of a single cell, is what suffocation actually is. So now we have a crowd of protons straining to return, and exactly one place they're allowed through. That place is the 5th structure, ATP synthase. As the protons stream back through it, part of it turns, and that turning is enough to press ADP and a phosphate together into ATP. Proton by proton, the crowd empties out, and ATP builds up. It turns, yes, but don't picture anything made of metal. Think of something soft and biological, rotating slowly because a crowd is pushing through it. This whole idea, electron flow building a proton crowd and the crowd making ATP, has a name: chemiosmosis. And the chain plus ATP synthase together, the full process, is called oxidative phosphorylation. When Peter Mitchell first proposed all this in the 1960s, most of the field simply didn't believe him. Energy stored not inside a molecule, but in a gradient across a membrane. It was argued over for years. He turned out to be right, and it reshaped how we understand nearly everything alive. Now, this is where it gets interesting, because not every animal uses that proton crowd to make ATP. Think of a newborn who can't yet shiver, or a bat asleep through the whole winter. They carry a special tissue, brown fat, with a protein that breaks the usual rule. It opens a second door and just lets the protons leak back through, skipping ATP synthase entirely. No ATP comes from that leak. Instead, the energy comes out as plain heat. The same chain, run on purpose, just to stay warm. And I'd be lying if I stopped there and told you we understand all of it. We know the players, the order, the logic. But real questions are still open. Those complexes often clump into larger assemblies, supercomplexes. And exactly why is still being worked out. So is the fine control of that proton leak we just saw. None of it is settled. And that's fine. A working picture with honest gaps in it beats a tidy story that pretends to know everything. So let's hold the whole thing in one breath. Loaded carriers arrive. They pass their electrons down a line of complexes. The complexes crowd protons onto one side of a membrane. Oxygen waits at the end and turns into water. The crowd rushes back through one gate. And that rush is what makes your ATP. Carriers, complexes, gradient, oxygen, water, ATP. That's the last step, and it's the one that does the most, which leaves one question we've circled the whole series without answering head-on. Next time, that's the whole episode. Why we breathe, what the oxygen is really for, and what happens in the small, strange moments when there isn't enough of it.